Welcome to EDU World Space.
Okay, so we're doing chapter 32, problem 72. And we have a slab of thickness D whose two faces are parallel and has an index of refraction N. As a ray of light incident from air onto one face of the slab enters, ray A reflects directly off of it, like this, shown at angle theta 1. Ray B goes through this, travels a distance L after reflecting once inside, and then gets refracted out again, a distance D away from ray A. Cool. So part A here wants us to derive an expression for L and D based only in terms of D, the thickness of the slab, N, the index of refraction, and theta 1, incident angle. Okay, so to start this out, we're going to set up our Snell's law equation. We can neglect this N because it's air. So then we can solve for sine theta 2 as sine theta 1 over N. So now let's look at our actual triangle here. And now doing some geometry, we should see that cosine theta 2 is given as is given as D over L over 2. So if we rearrange that, we should see that L is given as 2D over cosine theta 2. So if we use the Pythagorean trig identity, this is given as 1 over the square root of 1 minus sine squared theta 2. And now we can plug in our relation, and we should see that this comes out to being 2nd over square root of n squared minus sine squared theta 1. And this is our expression for L. Cool. So now let's go into D, and let's look at how we can relate this. So if we look at the sine of theta 2 here, that's given as the opposite over the hypotenuse. The opposite here is D over 2. So we can write the sine of theta 2 as D over 2 over L over 2. Or we can relate this as D being L sine theta 2. Perfect. So now we already have an expression for sine theta 2, so we just have to plug that in. We also have the expression for L. We plug that in. So we should see that this comes out to being 2D sine theta 1 all over the square root of n squared minus sine squared theta 1. Cool. And this equals D. Okay, so now for part B, wants us to check that this makes sense for the incident angle being perpendicular, so theta 1 being 0 degrees. This is part B. So if theta 1 equals 0 degrees, we should already see here that this equals this part right here equals 0 degrees, so we're going to be left with 2nd over n, or L, equaling 2d. That makes sense because that means that coming straight down, coming back up, that means the beam travels 2d. Okay, we're off to a good start here. Now let's look for d at theta equaling 0. Well, we have 0 up here. That means there's going to be 0. The whole thing is going to be 0. That also makes sense because it shouldn't travel any horizontal distance at all as it reflects back. So yeah, these equations make sense, so that's good. It's always good to double check these on test cases where we can easily confirm if they make sense or don't.